Okay, our next example is calculation of field outside a uniformly charged spherical shell. Now consider this one to be a spherical shell of radius capital R, and this shell has charge q, small q, spread uniformly on its surface, and our problem is to find field outside this shell at some distance small r from it. So let's see where we need to find the field. This is the point where we need to find the field, and its distance from the center is small r. So this charge distribution has a spherical symmetry, and if it has a spherical symmetry, we can predict the direction of field. Field lines is known to us. This would be the pattern of electric field lines. In such cases, the field lines would be directed radially away from the center. They may even be radially inward depending on whether the charge is positive or negative. So here, this is the direction of field. Our problem is to find the field at this point. Now at everywhere at distance, the same distance, this distance is small r, at same distance from the center, the field will remain same. So we can draw a Gaussian surface. Gaussian surface of radius this one, small r. So let's draw that. This broken line shows our Gaussian surface. It has radius small r, and we'll be finding flux through this one. Now note, at every point on the Gaussian surface, electric field has the same strength. This E over here, E over here, even at this point, same value of E. Let's see the direction of normal. This normal also points in the same direction as the field. So at every point on the surface, electric field vector and normal, they are in the same direction. Angle between them, theta, is 0. We can calculate the flux through it. Flux by the basic formula Es cos theta. So flux through this surface phi is Es cos theta. E, the electric field, it has same strength of all the points, this E. Area of the Gaussian surface, 4 pi small r square. Theta is 0, so cos 0 is 1. This is the flux through this Gaussian surface, which has been shown by this broken line. Now let's see the charge inside this Gaussian surface. Now all the charge which is there on the spherical surface, it's well within the Gaussian surface. So net charge inside this Gaussian surface is all the charge on the shell. So Q inside is Q. Q inside, charge inside the Gaussian surface is Q, all the charge of the shell. Now let's use Gauss law. By Gauss law we know that net flux is charge inside divided by epsilon naught. We have the values of flux phi and Q inside from equation 1 and 2. So substitute those values. This is what we'll get. E into 4 pi r square will be equal to Q by epsilon naught. From here we'll have the formula for Q. For E. This is our formula for electric field. So electric field outside a uniformly charged spherical shell, E, is 1 by 4 pi epsilon naught Q by r square. This formula is quite similar to that of a point charge at distance r. So we may conclude that whenever we have to calculate field at any point outside the shell, we may assume that all the charge of the shell is concentrated at its center, and we can treat it as a point charge.